his laptop, I guess. Okay, you're on. Okay.
Thank you. So I'll be talking about near optimal bootstrapping of hitting sets. This is a joint work with Mrinal Kumar and Anamai Tengse. Some of you who were at Duckstool, this is going to be a very similar talk. So the talk is going to be about algebraic circuits. So algebraic circuits are objects of this sort. They compute a polynomial in the natural way. I'm not going to go more into this. So the weird thing that happens with the new Apple thing, it just blurs every. Yeah, so I'll focus on just formulas, just for simplicity, but almost everything that I'm going to be saying today just works for any reasonable class that we care about. So there's a tree made up of these things, but I'm going to sort of define the formula size to be the number of leaves of the formula. And this is up to constant factors, so it doesn't make much of a difference. The reason I'm going to use this as the measure of complexity is because it sort of behaves nicely when we do compositions. That is, what I want to say is that if I have a formula computing f, and to its variables I plug in formulas of small size, then the total formula size sort of becomes a product, where it's just the size of f times the largest size of g. It's just easier to see if it's working, if you work with the number of leaves. That's the only reason. And we'll use the notation formula of nd comma s to refer to the class of all n-variate polynomials of degree at most d that are computable by formulas of a size at most s. And similarly, if I write circuits here, I mean, we know what that means. Okay? So the polynomial identity question is that, you're given a formula of this type, and then you want to know whether the polynomial computed by it is the zero polynomial or not. So there are two versions of this. One where you basically are given the formula in the sense that you know what the wirings are, what the constants, etc. are, so that you can inspect the formula and then make your decision. Or the stronger form is what is called black box identity testing, where you're provided a black box with some very basic parameters to sort of say that in this black box is a formula that has these parameters, and the only thing you can't really do is you have evaluation access, and that's what you do. So basically this is equivalent to the question of constructing hitting sets for this class, which is just to recall, a hitting set is basically just a list of points such that every non-zero polynomial in this class is guaranteed to evaluate to a non-zero value on one of these points. Okay, cool. Okay, so now the goal is therefore to construct hitting sets. So first let's ask ourselves, do there exist hitting sets of small size? And a simple counting argument will basically say that as long as your model is anything reasonable, that is, the description of your model is small, there will always be non-explicit hitting sets of polynomial size. Okay, whether it's formulas or circuits or whatever. Of course, what we want to know is, are there explicit hitting sets of small size or not? And there is a trivial hitting set, but this is bad in the sense that it follows from this sort of Or-Demelo-Lipton-Schwarz-Zippel lemma, which basically says that if you have a non-zero polynomial of degree d, then it will evaluate to a non-zero value on a grid of side length d plus 1. So if you just take a grid of side length d plus 1, then this is already going to be a hitting set for any degree d polynomial, irrespective of whether or not the size is at most s or whatever. This is completely independent of the size. So we have a sort of a explicit hitting set, but this is a trivial exponential sized hitting set of this much size. And so the question is going to be are there small hitting sets if I know that I'm working with formulas or circuits or something of bounded size? Okay. So earlier this year, or later last year, so Agrawal, Ghosh and Saxena proved this really cool result, which says the following. So let's assume the following. So let's say that, suppose for every s bigger than or equal to n, you look at the class of circuits that have the size s circuits of degree on n variables, and I'm just going to assume that the degree is bounded by the size of the circuit. Okay? And suppose you can construct a hitting set of size which is something like s plus 1 to the root n. So think of it as saying that the trivial hitting set must have had size s plus 1 to the n. And now we are saying that you want to improve the exponent to something smaller than root n. Okay, and suppose you could do this. Then they showed that you can actually use this to construct an explicit hitting set for almost polynomial size, where this tiny is a really slow growing function. If you care about what this function is, it's a double exponential in this log star function, where log star is defined as the number of times you need to keep taking logs for it to drop below 1 or something. What's a few log star among friends? So this says that if you have some sort of not too bad hitting set, then you can somehow use this to construct a really, really strong hitting set. And what we do in this work is improve this in two aspects. So the first aspect is that suppose you could give me a hitting set which is sort of barely non-trivial, in the sense that the exponent is, the trivial bound would have been n, but I just want anything better than n. So the point not one is no special number, it could be any number there. In fact, you could even put a 1 over log n or something. It's just that just beat the trivial hitting set by whatever amount, and we can get the same sort of conclusion as AG has got.
Half times s plus 1 to the n.
So the thing is, so basically you need to make some dent in the exponent. So that is, you're sort of, it's a question of how much in factors of s are you saving. That's it.
Can you get gain from constant size examples, or it's not enough?
So in fact, this n, even if you can do this for, let's say, like n equal to 2, this is fine.
The D and S are being constant. Is there a version of these two results that
So that
where you have bars like the D and S?
So I can write the statement, but it will sort of not be very useful in the sense that in the course of the proof, we sort of crucially use the fact that we are going to use this hypothesis for a lot of circuits, and there will be points when the degree and the number of variables the degree and the size will get very close to each other. So I would need the hypothesis, like for example, if it is the case that you're working with circuits of much smaller degree, then we trivially know sort of how to, if degree was much smaller than s, then we already have the trivial hitting set already seems to be better. But the proof will use regimes even when D is very, very close to S. So which is why I'm stating this in this regime. Yeah.
So all you need is like a little O of 1?
Sorry?
So all you need is like a little O of 1 advantage?
No, that thing could be 1 by log n if you want. N minus 1 by log n that will also give the same conclusion.
But probably it's not going to be 1 over s or something.
Yeah. So the thing is, I don't want the exponent to have anything to do with s. This is going to be very crucial. Like the gain is like in the n.
Like what if it's like 1 over 2 to the n, for example?
Sure. That's fine.
That is fine.
Yeah.
Because you want it for n equals 2.
Yeah, I just want it for, think of n, the hypothesis is going to start with n equal to some constant, and all I'm saying is that just beat anything non-trivial, but for every s, that's the important part.
N is a constant in the hypothesis.
Here.
It can be growing.
Yeah, here, I should have put it as circuits of s comma s comma s, I'm sorry, yeah. Sorry, should have made this. Okay, so this is one improvement, which is we just improve what you need in the hypothesis to get the same conclusion. And another thing that comes out of our proof is that the same result also holds if your hypothesis works for, let's say, some restricted class, like say formulas, or even branching programs or something. Basically, as long as you have a class which is sort of well behaved under compositions, projections, sums, and so on, this result will just hold. Okay. By the way, what time do I stop?
5:05.
Okay, cool.
What does explicit mean?
So, okay, good. So, by explicit, what I mean is if the final hitting set is of a certain size, there is an algorithm that runs in poly in that size that outputs that hitting set. Okay. So a very, very high level view of how this proof works is that it's just going to make use of this hardness versus randomness paradigm. That is, it's sort of well known that the task of constructing non-trivial hitting sets and the task of constructing explicit lower bounds are very intimately connected to each other. And so to go from a non-trivial hitting set to a lower bound, this was observed by Heinz and Schnorr and Agrawal. So that's this part. And to go from an explicit lower bound to a hitting set, so this was observed by Cabinets and Impagliazzo. Okay. And what we are going to do is basically just keep going round and round this thing. So what we'll do is we'll start with a non-trivial hitting set, get a decent lower bound, use that lower bound to get a slightly better hitting set, and get a better lower bound, and we're just going to keep repeating this process. Okay. So in order to describe it, I first probably need to mention what Heinz and Schnorr did and what Cabinets and Impagliazzo did. So I'll spend a fair amount of time trying to give an exposition of those results, and then see why you can actually do this, and also see why something like this seems to be unlikely in the Boolean world, but in the algebraic world you can somehow mint money. Yeah. Yeah. Okay, cool. So I'll go into the preliminaries. It's just the hardness-randomness trade-offs. So the easier thing to describe is the Heinz and Schnorr thing. So I'll do that first. So suppose we knew that we had a hitting set for some class C. Okay, hitting set here, and what is the definition? The definition says that every non-zero polynomial must evaluate to a non-zero value on one of these points. So the contrapositive of this is that if I can find a polynomial that is actually 0 on every point in H, then by definition it cannot be a member of this class. Now, ideally I would want to say, okay, this gives me a lower bound, but it could not be a member of this class for a stupid reason, in the sense that maybe the degree is larger than D. So in the sense that, so what Heinz and Schnorr said was like, if your size of the hitting set is not too large, then you will be able to find one polynomial that vanishes on all these points of small degree, and that will tell you that it's not a member of this class because the size required for it is large. And this gives you a size lower bound. Okay? And there's a lot of room in choosing how many variables versus the degree you want here, and this is going to be crucial in our PIT construction. Okay, so this is just a one slide overview of Heinz-Schnorr. Cool. So now I'm going to go into Cabinets and Impagliazzo. This will take a bit more time, but this is going to be the informal statement, which is that suppose you knew that Q was hard enough, in the sense that it required large circuits to compute it or something. Then if I, in place of x1 through xm, I substitute values, I substitute this Q, but not on disjoint variables, but on almost disjoint variables, this will somehow preserve the non-zeroness of the polynomial. In the sense that it's hard for a small circuit to figure out that what is plugged in is some correlated versions of a hard polynomial. So this is like an algebraic analog of the Nissan and Wigderson hardness-randomness trade-offs in the Boolean world. So maybe I'll just take a few minutes to sort of describe what this almost disjoint means. These are going to be defined by what are called combinatorial designs. It's possible a lot of people know this, but I'm going to do this anyway because it's cool. So combinatorial design is just a collection of subsets of a universe such that their pairwise intersections are small. Okay, so formally, I will say a collection of sets is an LKR design, to mean that L is saying that these all come from a universe of size L, and K is saying that each set is of size K, and R is a strict upper bound on pairwise intersections, where here I is not equal to J. Okay, and so these are called combinatorial designs, and we would like to construct such designs. There are plenty of ways to do this. You can just use the probabilistic method to do this if you want, and there's a way to phrase it in terms of codes. And what I'm going to describe is one sort of very hands-on construction which will be useful for what we do, which is, it says that for all L that is bigger than K squared, there are always going to be designs of this many sets. Like, think of L as just being K squared. So there are going to be designs of K to the R sets that achieve these things. And it's a very simple construction, which is what we are going to do is we are going to assume that L over K is a prime or a prime power and identify this with a field. And I'm going to look at basically like f cross f. That's going to be my universe, but I'll restrict myself to maybe the first k columns. So I have a universe of size L. And every set is going to be defined by a univariate polynomial of degree less than r. And the set is basically just the graph of this polynomial. So it's just it's just a collection of points I comma p of I where you range I from 1 through k. So clearly each set is of size k. They all belong to a universe of size L. And so different polynomials will give rise to different sets. And just this basic fact that 2 degree r minus 1 polynomials can agree in at most r minus 1 places tells you that the pairwise intersection is going to be small. It's an extremely simple construction, and this is the construction that we are going to be using for the thing. Are there any questions so far?
Do you need the algebra of the construction, or you don't care?
There'll be points when so there'll be points when it's important that this is k to the r and not 2 to the r. That's the only thing, but otherwise we don't really. Yeah. Okay, cool. So now that we know what this is, the notion of pairwise sort of almost disjoint or whatever. So I'm going to use this notation just to simplify things. So Q of L, K, R, I'm going to think of it as a vector of polynomials, which are basically what we want to plug in the Cabanets-Impagliazzo regime. That is, I want to plug in the evaluation of Q on almost disjoint sets. What I'm going to mean by that is there's going to be some set of L variables, and this is just it's just the Q applied on each restriction of these L variables depending on what your design is. Okay, this is just notation we'll keep using again and again. So, good. Okay. So here is the main lemma of Cabinets and Impagliazzo. It says that let P be some non-zero polynomial of degree capital D. And it has a small circuit. And suppose Q is a k-variate polynomial of individual degree less than D. By that I mean the degree in every variable in Q is less than small d. And suppose it so happens that when I plug this in, I got the zero polynomial. Then it must be the case that Q has small circuits. Okay, this is the key lemma of Cabinets and Impagliazzo. And I'll just give a quick proof of this because we'll have to come up with a version of this for formulas or ABPs or something. Okay, so here's what you do. So you start off with P, which I know to begin with is a non-zero polynomial. And I want to make the substitution, but I'm going to do the substitution slowly. So the first thing I do is replace x1 by the corresponding Q. Maybe it remains non-zero. Now I try to do x2. Maybe it remains non-zero. Now I try to do x3, and maybe at this point the circuit suddenly became zero. So I'm going to step back and sort of keep and tell myself that x3 is going to be an important variable and the set S3 is going to be important. I basically want to get rid of everything else that's happening right now. So right now I have a non-zero polynomial, which let me call P tilde, which depends on the x variables and the y variables. But I'll split it in sort of what I want and what I don't want. So I'm going to write it as x3 and the rest, and similarly y restricted to S3 and the rest. So the first thing we'll do is we'll get rid of the x rest variables by plugging values such that the non-zeroness continues to hold. So now it depends on just x3 and the y variables. The next thing I want to do is get rid of the y rest variables by plugging in values such that non-zeroness is preserved again. Now the point is earlier, these were all Q's evaluated at these subsets. But the moment I substitute everything outside of S3, whatever this polynomial is, it's going to depend only on the variables that actually belonged in S3. And so therefore, this is, I don't care what this polynomial is, but it's some polynomial of individual degree at most D that depends on at most r minus 1 variables, because I know that the pairwise intersections are small. So what I'm going to do is I'm just going to brute force and say that no, let me just write down a trivial circuit for that at these points because I can afford to, because r minus 1 in some sense is small enough. So let's just compute the size of this whole thing, and let's call this polynomial P prime. What's the size of this whole circuit? So the size is like, I started off with a circuit of size S, and now I need to plug in whatever is at the bottom. And what I need to plug in is some polynomial of individual degree at most D on r minus 1 variables. The number of monomials is d power r minus 1. Each monomial to write down, I might need something like dr. So this is the size that I'll require for each of these small slivers. So that tells me that the total size of p prime is small and the degree is also small. Okay, we made some progress. Now what do we know? If we replace x3 by q, this polynomial is becoming 0. That means that x3 minus q must divide this polynomial p prime. And at this point, you can just use the factorization algorithms to sort of say that factors of small circuits are small circuits and extract x3 minus q. You don't really need Kaltofen's result here because here we only care about the existence of small circuits for factors. We don't really care about an algorithm to get a small circuit. So there's a simpler proof of Peter-Burgiser. So you could just use this and pull out x3 minus q and set x3 equal to 0. And that basically finishes the proof of Kamenetz and Pagliazzo. So just to write down, if this happens, this is a formal statement. That is, the size that you end up getting is going to be whatever the size of this p prime is, par order 1 because of whatever this factorization algorithm does. Are there any questions so far? Okay, cool. So basically now what I want to do is, this is what happens in the circuit world. This hardness versus randomness trade-off, but ideally we would want to do this over, say, formulas or ABPs or something. And let's ask ourselves what goes wrong. And okay, sorry, before this, let me just write the contrapositive, which is just to sort of put it in the perspective of what we had last time, which is say that if Q did not have small circuits, if Q was hard enough, then the non-zeroness is preserved. So now, why does this not work for other models like formulas?
Not everything is closed under factorization.
Right. So the thing is, I do not know. I know that factors of small circuits have small circuits, but I do not know if factors of small formulas have small formulas. And this is the reason why I cannot apply. If I was working with formulas, I cannot apply Kaltofen. Or
what about ABP?
Even ABP, we do not know. Both these things seem to have an end to the log n blow up. Just based, this is the best upper bound we can prove currently.
But for ABP, you would expect?
I don't know. I would think it should be closed under factoring, but we don't have a proof currently. But I just want to get I just don't want to do factoring, basically. So let's step back and just tell ourselves that so far, if we were working with formulas, P prime has a formula of this much size. Up until now, everything is fine. Okay, I can't compute Q, or at least I do not know how to compute Q, so I'm going to try to do something else, which is to compute a multiple of Q. So basically what I want to do is, in some sense, P prime is already a multiple of Q almost. That is, if I can set x3 equal to 0, then I would compute something which is a multiple of Q. There's just one catch, that it's possible that P prime is divisible by x3. But you can use interpolation to sort of divide it out and then make your substitution. And right, so what you end up getting is that if it is the case that if you start off with a size s formula, and such a substitution ended up giving you the 0 polynomial, I may not be able to say that Q has a size small formula, but I'll be able to say that a low degree multiple of Q will have a small formula. Okay? And so, okay, cool. So what's the contrapositive of this? This is like saying that if Q has the property that it's hard in a more robust sense, that is, it's not just that Q is computable by small formulas, or it's not computable by small formulas, that low degree multiples of Q are also not computable by small formulas, then this gives you a way of preserving non-zeroness and sort of doing this. Okay, now why would something like this be useful? The important point is, if Q is hard because it vanished on a hitting set, then multiples of Q also vanishes on a hitting set. So they would also be hard for the same reasons. And this is what we are going to keep using. So we are going to build hard polynomials that come from hitting sets, because that way I can use the robustness of this hardness. Some will say that it's not just that Q is hard, but as long as, for some slack, even multiples of Q will be hard. And basically this is going to allow us to do the hardness-randomness trade-offs even for models like formulas or ABPs or something. Okay. Are there any questions so far? So this is, at least this should sort of say that, an analog like this should hopefully work for formulas if we start off with a good Q. Okay, excellent. So, right, so this gives us a way of sort of taking a hitting set for k-variate polynomials, use that to construct a hard polynomial, and somehow use that to do a variable reduction and therefore give a hitting set for m-variate formulas. And this is something we're going to be using a lot. I'll make this more formal. Okay, so here is a typical template for this hardness-randomness trade-off. Okay, the hypothesis will often say that, I have a hard polynomial, k-variate hard polynomial that's usually a little harder than what you want to construct a hitting set for. Okay, so if you want a hitting set for, say, MSS, you will need something that is sort of something like s to the c hard, where c is some constant or something. Okay, and what do? You first construct a design, and then you use the hardness of Q to argue that this sort of substitution preserves non-zeroness. And once you do this, this must be M, not L. Sorry, this must be M. So once you do this, you're left with some polynomial on just L variables. So just brute force over that. And this is how the typical sort of hardness randomness thing works. So in our case, what we are going to have is the hypothesis is not a hard polynomial, but the hypothesis is going to be a hitting set for some smaller L. So we do the same first step, but now we use the hypothesis to construct a hard polynomial Q. We do this from Heinz-Schnorr so that we have something that is more robust. And then we'll sort of say that, the non-zeroness is preserved. And finally, one last step, instead of brute forcing over this, I can just use the hypothesis again, because this circuit will turn out to not be like too large. I mean, it will be smallish. So you can use the hypothesis again, and you somehow start with some hitting set, and you can somehow get a better hitting set for a larger size. I mean, for a larger number of variables. And this is basically what we're going to do, and we are just going to keep doing this again and again. Okay.
So if you look at it, I don't know, if this is top down, maybe if you look at it bottom up, this would be an iteration of a basic PRG.
Yes.
You keep composing
exactly.
it with itself.
Exactly, yeah.
What is it?
So if you look at it from the bottom up, this looks like an iteration of the basic PRG. So at every step, you're going to apply a Nissan-Wigderson design, You keep doing this, and at the bottom, you're just going to use your base hypothesis at those points.
No, but in every step, there is an annihilator also. In every step, you are using Heinz-Schnorr.
Yeah, so the choice of the polynomial Q is because of Heinz-Schnorr, but you're essentially doing...
Right, so you're composing two hitting sets, but in the middle, there is an annihilator also.
The annihilator is the Q.
You don't need a hitting set, you can just use like generators and compose them. But actually don't need to produce the hitting set over and over again.
The construction uses it, because you take the hitting set, you get a new polynomial, you turn that into...
Oh, yeah, sorry. Yeah, you're right.
You don't actually need a hitting set, you can just keep working with generators where they see getting better and better or something like that.
Yeah, I mean, anything reasonable should work. I mean, yeah.
This extra robustness it was only needed for formulas and APIs.
Yeah. So if you care about circuits, you don't need any of this. You could have just done.
So in the circuits world, could you have done white box to white box?
No. So yeah, it's for a technical reason. Anyway, we'll see. Okay, let me rephrase. I do not know if we can do it. I mean, okay. I don't know of a way of starting with the hypothesis being a white box thing to get a similar white box. Good. Okay. So let me talk a little bit about why does bootstrapping work? I mean, this seems like something weird is happening. Like we're just getting something for free, and I want to talk a little bit about it. So let's start with the regime when you want to do PIT for a poly-size circuit. That is, you start off with a circuit which is something like m⁵ size or something. Okay. So for this, what you would have to do is find a k-variate polynomial where k is like order log m. Okay. Which is sort of reasonably hard, so that you can do a variable reduction from m variables to something like log squared m variables. This is what you would want to do. Now what bootstrapping is suggesting is just saying that let's look at this new polynomial that we get after this variable substitution, and what is really stopping us from doing this again. The problem is that right now, earlier S was polynomial in M, but S prime is going to be slightly larger than S. But if I look at it in terms of the number of variables, this is already exponential in the number of variables. And this feels like, this is going to be a problem, because now in order to apply this again, I will need to find a hard polynomial which is sort of a k-variate hard polynomial where k is now going to be like log L, but then it has to sort of be doubly exponentially hard in terms of k. Sorry, this should be k again. Okay, that's sort of what you want, and this seems like, this is feels like a losing battle, because for instance, if you are doing this in the Boolean world, I mean, you can't hope for hardness that is beyond exponential, because every Boolean function on L variables will have a circuit of size at most 2 to the L. But here the point is, in the algebraic world, you can play with the degrees. I mean, it's possible that you are working with L variate polynomials, but of possibly large degrees. So it sort of makes sense to ask if, does this polynomial have a doubly exponential in L size circuit? Maybe because the degree is also of the order of the same thing. And this is really, in some sense, this is sort of what allows us to do this bootstrapping. And so the message of this whole thing is that there is really nothing stopping you from doing this bootstrapping again and again. You just need to be using the degree of the polynomials you're working with as well. And this is important. This is in my opinion, the key difference between what is happening in the algebraic world versus what is happening in the Boolean world. Okay. So in the remaining 10 minutes, what I want to do is I want to try and give a full proof. And the full proof will basically follow this plan. So we'll start off with a hitting set that's sort of barely non-trivial. We'll start off with this assumption that for every s greater than or equal to n naught, we have a hitting set of this much size. From this, I'll show that you can get to a slightly better state, which is now your hitting set size is going to be n by 50 instead of n minus 0.1 or something like that. But this n1 will be larger than n naught, something like n1 will be like n naught par 10 or something like that. Okay. The next step would be to get to a point where it is something like polynomially, the exponent is sort of polynomially better than brute force. It's like 4th root of n or something like this. And at this point, we are just going to use the machinery that AGS, Agrawal, Ghosh, and Saxena had. And they had this nice lemma that says that suppose you had a hitting set where this g of n was substantially smaller than root n. I'm using n to the 1/4 just to make the calculations easy. Okay. Then you can get a new hitting set for something like that looks like, where the exponent looks like g with a log inside, intuitively. So basically what this allows you to do is that you can now repeat this process, because the new h of m will also satisfy the same hypothesis, and you can keep inserting logs inside the running time, inside the exponent. And this is what they call bootstrapping, and that will give the result that you want. Okay.
So if you're using the other result, then how do you make it work for formulas and?
So Agrawal, Ghosh, Saxena worked only for circuits.
Right.
But if you replace the vanilla version of Cabinet-Simpagliazzo with this version, this gives you, this just recovers Agrawal, Ghosh, Saxena from this thing. Yeah. So this is going to be the plan of the rest of the thing.
You made a comment about n naught can be 2 also.
Yeah, so here the n naught can be, you can start off with even n naught being 2 and so on, and at one step of the iteration will increase it by something like n naught par 10. One step of the iteration will again increase it by another n naught par 10. But from here on, the increase is exponential. And eventually in log star steps, you will reach whatever s that you want. That's the high level picture of what's happening.
The increase also in the degree will be exponential.
It's a question of compared to what? Like the
previous degree.
Yeah, but so we'll see what happens in the proof, and things will be clear. Okay, so what I'm going to do is I'll first give a proof of this lemma, which is which is basically what AGS had, and we'll see what happens. So this is the formal definition, formal statement of AGS's lemma, which is that suppose n is large enough. In this case, it has to be large enough by some amount. And you had a hitting set that was sort of better than root n. So here I'm going to work with n power 1/4 just to make life easy. Okay. Then you have a hitting set for whatever n you start off with. You have a hitting set for m variate polynomials where m is exponentially larger than n. But the running time doesn't degrade by too much. So somehow your the number of variables increase massively, but the hitting set size sort of degraded very, very little. And if you just start with this and keep applying this process again and again, okay, this blurriness messed the whole thing up. But it's sort of easy to sort of see that no, if you start at whatever n naught and you now repeat this again and again, you will see a double exponential in log star coming up. It's a simple calculation. I'm not going to bother about this. Okay, so what's the proof of this lemma? Okay, I'm going to give we're going to follow the template that I described earlier. If you don't follow it once, it's fine. I'm going to do the same thing 3 times with slightly different parameters, and we'll see what happens. Okay, so this is the hypothesis. I have an s to the gn sized hitting set for this class where g of n is at most n to the 1/4 over 10. So you first pick a design, and these design parameters is really what will change in the 3 things. So here it's like the universe is of size n, each set is of size root n, and the pairwise intersection is like n to the 1/4.
So the n here is just, I should think of it as some fixed constant or something.
Not in this. So this is the bootstrapping lemma where we'll keep applying it again and again. So there will be points when this n also becomes growing.
Right, but do you need this assumption for all n in order to deliver the conclusion for all n?
Yes. So right now, let's say that n is some fixed thing. We have somehow constructed a hitting set up till size n, and I now want to construct a hitting set for size m. Not size. I mean, I have n variate polynomials. I have a hitting set. I now want to construct a hitting set for m variate polynomials where m is exponentially larger. Okay. So I start with such a hitting set. Now what I do is I use the hitting set for size s.
It may help if you point out that n and s should be thought of as independent variables.
Sure. Yeah. N and s are 2 independent things. Yeah. Okay. You start off with a hitting set for size s power 5 and use that to construct your hard polynomial. Okay. This is the Heinz-Schnorr step, and the individual degree will turn out to be whatever the size of the hitting set is divided by k, the number of variables. Okay. So I'm using a hitting set on n variables, but constructing a polynomial that just depends on k variables. But just think of it as q is just masquerading to be an n variate polynomial when it's really just a k variate polynomial. Okay. And you use the hardness claim to sort of say that, I want to say that this preserves non-zeroness. Now why is that? Notice that q vanished on a hitting, we need q to vanish on a hitting set of size d prime s prime for this claim to work. And fortunately, our choice of s power 5 was enough to account for these things, and then Bob's your uncle, you're fine. So we know that the non-zeroness of the polynomial is preserved. And at this point, we just observe that how large is this polynomial even after the substitution. The old size was s, and this is some polynomial of individual degree, at most this in like k variables. Okay, so it has at most this much size. So put this all together, and this you can sort of use the hypothesis again for, and that completes the proof of the main bootstrapping lemma. So this already tells you that if you could do s to the n to the 1/4, you can get to s to the tiny of s. Okay.
So what is the, do you actually need to construct q to get the?
Yes. Yes, because I need to, for this to be explicit, I need to sort of say what the hitting set is for the new guy.
Okay.
So I need to sort of plug in q via this.
Q
Yes.
on all inputs.
Yes. I'll need a circuit for q so that I know what to plug in.
So I guess what you need to do is evaluate q on
Yes.
the point
Yes.
of the hitting set? Or?
Yes. I basically need to. So whatever is the hitting set for the L variate case, I need to evaluate Q on the corresponding points and feed that as my m-variate heating set. So for that I need to know Q explicitly. Okay, so this finishes this part. So let's do this part, and this is going to be basically the same thing. So, okay, so this is the hypothesis we are working with. So I have an s to the g of n size heating set where g of n is like n by 50. And again, I want to get to the n to the 1/4 type regime. Okay. Now we are going to do a slightly different design. That is, k is going to be n, l is going to be like n squared, and think of r to be 10. I mean, intuitively, the point is I only need a stretch of something like from k to k power 10, so I can sort of afford r being very small. Okay. Good. Exactly the same thing. I mean, you work with you take the heating set for size s power 5 and somehow show that it's non-zero. Why does it preserve non-zeroness? Bob's your uncle. Yeah, and this will tell you that the non-zeroness is preserved after you make such a substitution, because you'll be well within the sort of guarantees you need. Okay. Okay, now what? Now the point is one thing seems to be that maybe we can try to use the hypothesis again, but we can actually do something even more stupid, which is I can just say that now this new polynomial is some polynomial on L equals, which is n squared variables, and its degree is not too large if you plug in the values. So I can just use Schwarzschild right now. I mean, like I can just say that there is a heating set of size s power 3L for this, and my m is so much larger that by saying that I have a heating set for s power 3L, I've already got to the sort of regime that I wanted to. Okay. In the remaining 2 minutes that I have, I'm going to give the proof of the last step. Again, same thing. So now we are going to start off with a heating set which is barely non-trivial, and I want to make progress here. And at this point, it's crucial that we are going to run this step of the proof when n is truly a constant. Okay. So some design parameters. Now what you do is you need to work with the heating set for formulas of size something like s power 300n. This seems like a very bad thing, but again, let me remind you that n is a constant. So this is something that is actually doable. Okay? And the reason I'm doing this is because the individual degree somehow happens to be slightly smaller than s power 300n. And this is the sort of regime I meant where I need to use this hypothesis when the degree is very close to, what is that? Okay. And so now I want to make this claim that it preserves the non-zeroness after the substitution. Now let's try to do this, but let's try to go through the proof. This will not work as is, so let's just go over the proof. What did we do? We said that if this turns out to be 0, then there is a small multiple of Q whose degree is not too large. Somehow the degree is not the problem, such that it is computable by a formula of this much size. Okay. Now let's ask ourselves, have we got a contradiction already? Now the point is, what do I know about Q? I know that Q requires circuits formulas of size s power 300n. So if this quantity was smaller than s power 300n, we are cool. But let's ask ourselves, is that the case? R equals 2 in this regime. So in this sense, the pairwise intersections are 1. But this already has a component which looks like a d squared in it. And d is very, very large. So this is going to give me something that's much bigger than s power 300n, and which seems to be a problem. So it doesn't directly work, but it just needs one additional observation, which is
R minus 1 is d, right?
Sorry? R was a pairwise, was an upper bound on the strict upper bound on the pairwise intersection. So here in this case, R was equal to 2. So there was d power r minus 1. D power r minus 1 is a number of monomials, and there's another d outside. So this is giving me a d squared, and that's currently a problem. So let's look at where did this term come from. It was the complexity to compute an r minus 1 variate polynomial of degree d. In our case, r is 2, which means this is the complexity of computing a univariate polynomial of degree d. To say that this requires d squared is stupid. So what we should be doing is sort of use just Horner's rule or something to actually come up with an order d sized formula or circuit or something to compute it. So this will tell me that the size of this multiple is actually much smaller than what we had. I mean, in the univariate setting. Okay, and then you plug it in, and Bob's your uncle, and yeah. So this tells you that non-zeroness is preserved. Once again, you can hit it with Schwartz-Zippel, and you get a hitting set of the size you want. Okay, and that's the full proof. Okay, so I'll just conclude with some closing remarks. Okay, so the first thing is that a similar statement also works if you start off with bounded depth models, except that your hypothesis and conclusion have to be staggered. Because every time you apply this recursive construction of the hitting set, I mean, you're going to increase your depth, and this you do something like log star s times. So you'll start off with a hypothesis for a larger depth circuit to get a final hypothesis for a smaller depth circuit. And this is something I want to mention, that it's absolutely crucial that whatever gain you have in the exponent is independent of s. So it almost feels like saying that if someone told me that there is an s to the log s sized hitting set for size s circuits, this seems like an awesome, I mean, this is of course better than brute force, but it's better than brute force only in the regimes when s is not too large compared to n. But it's crucial in our thing that there'll be points in the algorithm where you're working with s which is way bigger than the number of variables. And in those regimes, you're not beating brute force. And I don't know how to get rid of this. I would really say a nice question here is like, can we start off with a hypothesis which is more natural in the sense that suppose you had such a statement only for poly-size circuits. These are the sort of circuits we care about. Can you make something non-trivial? Can we make something non-trivial here? I do not know what the thing is. And finally, to obtain a hitting set for a particular size, I mean, like we start off with the base hitting set, but for several values for s prime, where this s prime will never be bigger than s bar tiny s in the proof, but we need several. And the reason I'm mentioning this is because I want to know if there is a hardness amplification type statement that works in this regime. And I mean, Carmesino, Impagliazzo, and so CILM actually have such a statement in the non-commutative regime, to sort of start with a sort of decent lower bound to a really good lower bound. And it seems like a hit, once you have a decent hit, I mean, barely non-trivial hitting set to super awesome hitting set, ideally it feels like you should be able to flip it around and convert it to lower bounds. And this is the reason why we don't seem to have a clean statement of that sort. So this is another question, and I'll just stop here.
I want to get back to my original question. So can you get an explicit description of this PRG or heating set generator from bottom up? So you seem to be constructing one heating set. It gives you, it creates by hand, a hard polynomial from which you compose with and get another heating set.
Yes.
And it also gives you another polynomial you compose with it. I mean, can you, this top-down description does not, clarify.
So we felt something very similar. So finally what we did in our last thing is that in the appendix we just wrote down the code to just, the code is supposed to just spit out what the hitting set for the final thing is. It does do this composition, but the thing here is that you need to pick a different hard polynomial at every level of this iteration.
But it's not that different.
But
same nature.
I don't have a more concise description of this as a top-down, bottom-up approach. But yeah, I'll think about it and get back.
Last question. Get tired. Okay.
Nutan?
This is one place where you seem to be able to get rid of caltofin. Do you see some application of this somewhere?
So I don't know how to do this for general hardness-randomness trade-offs, because I mean, unless we know that some of formulas are closed under factoring, it's in some sense possible that if it was not closed under factoring, maybe there are hard polynomials such that some multiple becomes easy. So I don't know how to get around that in the combinatorial.
Sparsity, for instance, this will happen.
Yeah.
So even though it sounds counterintuitive,
I mean, it's possible that there is a blow up. So
But an alternate way to ask it is there a different way of coming up with a function q such that every multiple of q is hard?
yeah, I don't know.
This comes up in our paper on proof complexity, where it's really important to have hardness not just for q but all its multiples. So so there are other contexts in which the need for this is there and is used there.
Okay, on that wonderful last question, stop.
Okay.